All right, so official aloha and welcome to this webinar about carbon in breadfruit. Again, my name is Donna. I'm the manager of the Hawaii Ulu Co-op, and we're super happy and honored to have Chad and Noah sharing about this important topic with us here today. And we will have a lot of time for Q&A at the end. So you can feel free to type your questions into the chat as we go, and we can make note
Hey,
of it,
Lucas, do you
or you
want
can hold
dinner?
your questions until the end. And please just go ahead and mute yourself if you aren't already muted, because if you're not muted, we can all hear you. All right, and with that, I will pass it over to Chad Livingston, who just completed his master's degree at UH under the supervision of Dr. Noa Lincoln. Congratulations, Chad, on your accomplishment, and we're all really excited to hear what you worked on.
Hey, great. Thank you. Thank you, Donna. It's exciting to be here. And yeah, it was exciting to finish. Um, before I get, let's see here, there we go. Before I get too deep into it, I was, of course, a part of Dr. Lincoln's lab. And in a lot of ways, the work that we did for my thesis built on the work of others. And so I'm going to turn it over to Noah for a quick introduction to kind of the broader work. So over to you, Noah.
Sure. Thanks, Chad. Yeah, so my name's Noah Lincoln. Been a professor at UH for about 8 years now, and a core piece of what we've been doing is trying to support breadfruit and the breadfruit industry through a variety of research directions. And a lot of that has focused on, improving farming practices in terms of nutrient management, pruning, disease and pest management, and things like that. Um, but yeah, with the increasing money availability out there from the USDA, finally taking things like, climate smart commodities and greenhouse gas mitigation through agricultural practices more seriously and starting to put money in that direction. We wanted to, try to support, I think what we all know to be true that, breadfruit has the ability to sequester carbon through farming practices and, try to start quantifying that. Both as a potential, right, for farmers to in the future receive direct payments as carbon capture, but also in terms of kind of the marketing and branding side of things, right, being able to really tell consumers how much impact eating breadfruit can have on our environment can also help, with things like market development and demanding premium pricing and things like that. And so ultimately we want to move more towards breadfruit agroforestry, diversified agroforestry. But from a research perspective, that's a lot more challenging and complex. And so we basically just started with the breadfruit tree itself. And that's really what Chad's work focused on, was looking at, the growth of the breadfruit trees and how much carbon they sequester as they go through their life cycle. And so, yeah, so we were really happy to work with a lot of the farmers that are part of the Ulu Co-op, and help to gather data from their trees was a big support in terms of this research. And then working with them again, to help disseminate these findings and get it out there. So, yeah, with that, I'll turn it back to Chad, and we'll let him share his results.
Okay, great. Thanks, Noah. I won't spend too much time on this. Dr. Lincoln touched on a lot of this in his introduction into how we got here and the need to really understand specifically the carbon benefit that ulu provides or breadfruit provides. Because there's just so many other benefits. It's an important part of Hawaiian culture, being a canoe crop. Most of the audience is probably very familiar with this, but just for people that maybe aren't familiar with breadfruit, the thing to note is that it is a carbohydrate source that grows on trees, and from specifically a carbon perspective, that's what makes it really interesting. Is something akin to a potato, but it's a tree. And so that's like, with that as kind of the backdrop, that brought us into this space. And so really, at its most basic level, the simplest way to describe the research that we did for my thesis was to answer, how much carbon is in a
I think we've lost Chad. Let's give him a few moments and see if he can come back. Turning off videos might help. Oh, looks like he just got dropped.
Okay. Well, I have his presentation and can take over, I guess.
Thanks, Noah.
Yeah. Can you see the screen?
Yes.
Okay. So yeah. So how much carbon is stored in a tree? I think is where he left off. And excuse me, I didn't put this slide deck together, so I will bumble through this a little bit. But essentially, the most common way to start looking at, carbon sequestration by trees is to utilize a practice known as allometry, or allometric equations, in which you can relate parameters of a tree that are easy to measure to larger parameters of the tree. So most commonly, you can relate the diameter at breast height, which is a really common forestry management measurement you make, which is just the size of the trunk at about 1.3 meters. And you can relate that to the total amount of biomass and the total amount of carbon in a tree. But how you get that total amount of carbon is the tricky part. And traditionally, what people did was go into the field and cut down the entire tree, cut it up into tiny little pieces, throw it into a big kiln, dry the entire tree, and throw that on a scale and get biomass. So a method known as destructive sampling, where you destroy the tree and then you basically measure it after the fact. With more modern tools, there are other options these days, including using kind of remote sensing methods. So things like photogrammetry or LiDAR, which is like an active sensing. You can actually build 3D models of the tree and use that to calculate the volume of the trees. But then even once you have volume, you still need to convert that to biomass, to carbon. And so there's a lot of work that goes into it. And consequently, there isn't a lot of allometric studies out there. They're common for forestry trees, so things like pine, where we're growing, right, tens of thousands of acres of a single tree. It's common to have allometric equations for those types of trees. But most of our crop trees, most tropical trees, and especially an underutilized crop like breadfruit, there's nothing out there in this sense. Um, yeah, so like I said, we basically use this concept of allometry, in which you relate something that's easy to measure to something that's harder to measure, and they're able to build out these relationships to start to get the answers that we're after. This is also what I just talked about. There's a lot of ways to get these measurements, such as through, again, kind of nowadays building 3D virtual models of a tree, or doing destructive sampling, cutting the tree up, drying it out, measuring it all on scales. And we kind of did a non-destructive method that is supported by the United Nations Food and Agricultural Organization. And basically, it's this picture on the left in which we take very detailed architectural measurements of the entire tree. So every branch of the entire tree, we measure the diameter, every single meter along those branches, and based on that are able to reconstruct a simple mathematical volume of the tree. And then we relate those volumes to what we're interested in, which essentially is the biomass and the carbon. So allometry, how accurate is it? Basically, the more narrow of a group you look at, the more accurate they are. So trees differ obviously by the species. They could differ by variety within the species. They could differ by where they're growing. A tree, same species, same variety growing in a dry climate will probably be a slower growth, but also a denser wood. And so it really depends on how broad of a group you're looking at in terms of how accurate these equations are. So when we're looking at something like pine trees in a forestry operation that are extremely homogeneous, right? All those trees are clones of each other. They're all growing in the exact same conditions. When people build allometric equations for pine forestry, they're on the order of like 99.9% accurate. Very, very tight predictions. But again, it takes a lot of work to build the allometric equation. And so what happens is people start applying them to broad groups of plants. And so these are some examples of really commonly used allometric equations in the tropics. And you see that under the description, right, they're very broad categories of trees, right? Pan-tropical broadleaf trees growing in moist conditions. And they're grouping every study that's ever been done of a pan-tropical broadleaf tree growing in moist conditions and lumping them all together to make one generic equation. The problem is when we look at, several generic equations that could apply to breadfruit, there's huge variation, like on the order of, 20-fold variation in the carbon estimate. And that type of uncertainty is so big as to just be useless, right? To say that a breadfruit tree might store anywhere from, 200 to 800, kilograms of carbon, it's a big spread, and not very useful. So we through this work, we are really hoping to refine these estimates and narrow in this big gap that we see in the existing equations. And so, yeah, so we'll walk you through the process real quick, and then get to the punchline. And so, yeah, so step one is to build out the volume of the tree. And as I said, we did this by breaking the entire tree into 1 meter long segments and measuring the diameter every meter along every branch. And that allows us to estimate the volume of each branch in these 1 meter segments. And then we can add them all up and get the volume of the tree. And yep, that's what he's showing here. So every meter along every branch on the entire tree, we get in there and take all these measurements. And that allows us again to calculate the volume of each individual little barrel, like that. Now, he really went all out on the animations here. And so again, we need to take this volume and start to convert it to what we're interested in, which is biomass and biomass carbon. And to do this, we have to then start to look at the density of the wood and the carbon density of the wood. But the thing is, as I think he displays pretty well here, that it's not constant throughout the whole tree. So when you look at a thick branch or a trunk, that wood is a lot denser than if you look at a skinny branch. And as a branch grows and it thickens, the wood tends to get denser, and it also tends to get more carbon rich. And so we worked with farmers or other people who were removing trees, and we take little cross sections of the branches that are called cookies, little tree cookies. And we use those cookies to measure the wood density and the carbon density of the branches at different diameters. And that's some of this data here. And so you can see it's a pretty tight relationship, that as the radius or the diameter, the size of the branch increases, it gets more and more carbon dense in response. The leaves also hold a good amount of carbon in a tree. And again, we use another allometric relationship where we can relate the size of the branch diameter, to the amount of leaves that that branch holds. And so same thing, we worked with farmers who are doing pruning, and we harvested a whole bunch of branches, and we looked at how much leaf biomass was on the branch and the diameter of those branches. And again, you get a pretty reasonable relationship, about a 91% relationship that relates that stem diameter to the leaf diameter, or sorry, to the leaf biomass on that stem. And so we can take all these different measurements and build out a mathematical model that takes all the measurements from the tree, calculates the volume, takes all those individual branch diameters and calculates the wood density and the carbon density, combines all of that into the woody biomass, and then simultaneously calculate the leaf biomass based on the diameter of every branch. And so yeah, so we built out very extensive Excel spreadsheet that kind of builds all those equations in and spits out our total biomass. And then we take that and we go back to the tree, and we're able then to look at how a tree, the size of the tree relates to the total carbon biomass of that tree. And this relationship turned out really tight for us. See that R square valued up in the corner, 0.998, is a pretty near perfect relationship. And so we can basically see, you know, based on the diameter of the tree, we can quite accurately predict the biomass and the carbon biomass of those trees. And when we look at it in response to all these other allometric equations that people have been applying to breadfruit, our study comes out pretty much right in the middle of all of that, which is kind of a good validation that you know, we're in the right ballpark, and that, you know, we are likely making a realistic estimate of carbon in breadfruit. So that's really good if you're measuring an existing tree. So if you have a tree growing and you want to know how much carbon is in it, you can use this equation and basically measure the trunk of your tree and get a really accurate prediction about how much carbon is in that tree. But what if we want to predict into the future and say, like, hey, we want to plant a big breadfruit orchard. How much carbon will that sequester over the next 20 years? And to do that, we have to start to understand the growth potential of breadfruit a bit. And so some of the work our lab did a while back with Khaleesi Mausio, we looked at habitat suitability of breadfruit across the state. We surveyed about 1,200 naturalized breadfruit trees across the state and used that to parameterize a model. And then we used about 50 farms across the state to validate that model and understand its accuracy, and basically get a sense of, you know, how well will breadfruit grow in different habitats. And that's what this map is representing here. So areas of green, dark green, are really good breadfruit habitat. Areas of red are really marginal breadfruit habitat. And then the white areas means breadfruit will not grow unless you modify the environment, right? So a lot of the leeward areas are too dry, but if you're willing to irrigate your tree, well, then it'll grow there. So this is kind of how well will breadfruit grow under natural conditions. And basically what we did is went out and surveyed about 300 trees of known ages across the state. And then we were able to look at the size of the tree based on how old it was. And then we broke this data set up based on how good the habitat was for breadfruit. And so we got, again, pretty good R square values, you know, up in the 0.9s or the high 0.9s, meaning that we're, you know, able to explain over 90% of the variation in growth based on these equations. And basically, we're able to then predict that based on how old a breadfruit tree is, how big its diameter is going to be. And then, as we already walked through, we can take that diameter and estimate how much carbon the tree stores. And then the final piece looks like he threw in here is the below ground biomass, so the roots and the underground component. And I'll just say really quickly, we did zero work on this. It is well beyond the scope of our project to start excavating breadfruit roots and measuring carbon in the roots. That would be uh, a lot of work. And we'd have to destroy a lot of trees. We'd need heavy machinery to dig out all the roots. It's not something we feasibly want to do. And so we basically used a large study that looked at what they call root to shoot ratios to estimate the root biomass. So we can take all this stuff together and again kind of build a model. And so now our model can throw in the age of the tree, the habitat suitability the tree is growing in, and from that, estimate the growth potential of the tree in terms of its diameter at breast height. And from the diameter at breast height, be able to estimate the total amount of biomass in the tree. From that, we're able to estimate the biomass in the roots and basically calculate out, the total carbon dioxide sequestration, um, you know, per per unit of interest. So we can look at, per tree. If we, talk about an orchard, we can look at per acre or per hectare. Um, and yeah, so this is essentially what Chad did. And so this is just one little scenario he ran. So in a nice high suitability breadfruit area, if you grew a 1 hectare orchard of breadfruit, which would be on the order of about 80 trees, after 20 years, you would have sequestered a little over 90 metric tons of carbon dioxide. Yeah, so again, we want to look a little bit more in depth into breadfruit as a whole. So this study that we're really just looking at carbon sequestration in the tree, is only one part of the total uh greenhouse gas, story of breadfruit, right? Because growing the tree is one part, but then you harvest the fruit, right? You might process the fruit, you distribute the fruit, so it has to be transported and stored. And so the whole value chain of going from farm to fork, has a range of greenhouse gas emissions associated with it. So we know that we're sequestering carbon in the tree while it grows. And so then the next steps are to look at like, well, how much emissions do we have in terms of the value chain? And is the trees sequestering enough carbon to offset the carbon that we're going to create along that value chain, doing the processing, the distribution, and all of that stuff? So we're actually talking with another master's student right now at Arizona State University, and she's interested in possibly doing some of that work. And then we can kind of look at breadfruit in comparison to larger studies that have done this for other food sources and try to understand, right, where does breadfruit fit compared to rice, compared to corn, potatoes, right, the other staples of our planet. So yeah, so this is step one, hopefully in some future studies to situate our indigenous crops and breadfruit in particular in terms of its greenhouse gas emissions as a food source. So on behalf of Chad, I would like to
Chad is
acknowledge
actually
myself.
here. Um,
Oh, okay.
able to come back. He's just on his phone. So maybe Chad, would you like to take the mic, and is there anything you'd like to weigh in on or add to what Noah shared?
No, it was great. It was like Noah was reading my script. I'm really sorry, guys. My home internet system just crashed. So, but I'm here on my phone, and so if anybody has any questions, I can answer those. But really, a sincere thank you to Dr. Lincoln and the rest of my committee and Manoa's Tropical Plant and Soil Science Department. They're very patient with me throughout all of this process. And then, of course, very huge thanks to Ulu farmers just for the work that they do every day, and to the Ulu Co-op for trying to, make this crop that I do genuinely believe is an important part of a climate smart future, getting that into the hands of more people. So yeah, thanks Noah. Thanks for pitch hitting for me.
Yeah, no problem. And I tried to go fast because I always think the Q&A is better. And so yeah, so we have quite a bit of time to kind of go into questions and discussion from the audience. And so yeah, we're happy to transition into that. And yeah.
Thank you, guys. Thank you so much. That was so interesting. We do have one question in the chat so far. Andy is asking if we can include fruit production in these calculations. Andy, do you want to unmute yourself and ask the question or explain it?
Sure. So we're talking about a static measurement on the tree, or not static because you're doing it over time, but you haven't really talked about the breadfruit itself, which presumably is going to be harvested. And how do you calculate the carbon that's contained in that?
Hmm.
I didn't hear you address that, so that was my question.
Yeah. And I guess when you get into carbon accounting methodology, there's usually a consideration, right, of how long does a product store the carbon in. So for instance, if you think of a pine forest, right, and we cut down those pine trees and that pine tree is ground up and turned into paper, and that paper is then printed out of a printer and ends up in a landfill, and then it decomposes and re-emits, right, that carbon dioxide into the atmosphere as it decomposes. You would have like some storage capacity associated with that paper, right? And maybe the average lifespan of the paper is 5 years from the time it's created until the time it ends up in a landfill and re-emits the carbon. So you might have 5 years of additional storage. Whereas if like you grew, I don't know, cherry and turned it into a beautiful armoire that goes into somebody's house and is kept as a family heirloom for like 500 years, right? That armoire, that same wood, is storing that carbon for an additional 500 years. So for the fruit, right? I mean, our assumption is that the fruit relatively quickly is eaten. And once we eat it, we digest it and we poop it out, and that carbon basically ends up back into our system pretty quickly. So the amount of time that the fruit is actually able to store the carbon, we assume is pretty short, and therefore don't include it in the calculations. But that said, if we wanted to, that habitat suitability model I showed you from Khaleesi's work does a pretty decent job at predicting yields. That's actually how we validated the model, was based on farm yields. So based on her model, we can do a pretty good estimate of how much poundage of fruit each tree would produce based on the habitat suitability. And we could then, take those numbers and convert that into carbon based on the fruit production. But again, how long does that fruit store the carbon for is the question. Because, once it gets eaten and consumed, that carbon mostly gets re-emitted into our atmosphere from one pathway or another. And just sorry, one last thing on that. What we are interested in terms of the fruit, right, is thinking about carbon sequestration on a per calorie basis, right? Because that's kind of the standard metric that people will measure food emissions from. Because wheat flour is a lot lighter than say an orange, but which one sustains us more, right, in terms of calories and nutrition. So most studies that look at food carbon emissions, they normalize everything by how much calories, right, is produced. So in that sense, we're very interested in the fruit production because how much carbon's being sequestered on a per fruit or a per calorie basis.
Got it. Thank you.
Hey Noah, for that breadfruit suitability map, what are the factors that go into creating or grading the suitability? Like the climate, the soils, the temperature, elevation. What exactly are all the factors?
Yeah, it's actually, I think Khaleesi is on the webinar if she wants to share about her work. But yeah, in short, all of that. So, I know, let's see, trying to pull up the paper real quick. So yeah, so temperature, rainfall, solar radiation, and then soil pH and the soil classification. And those were selected because there's a global database put out by the Food and Agricultural Organization of the UN called EcoCrop, and these are the parameters that they have available for basically every crop in the world. And so we, kind of use them as a baseline when we first created the model. And then we went out and subsidized that with a lot of our own collections across the state. But the idea was if we could build this model based on these parameters, we could go get these get relevant data from this database online, EcoCrop database, and then model any of our other crops as well. But yeah, you essentially hit it on the head. It's climate and soil.
Right on. Thank you.
No, okay, so just a little bit context. So on Molokai, we're trying to acquire for the community Molokai ranch lands, and I saw on the map Ulu is not in the Molokai ranch lands on the west side, but we've been talking to people that are wanting to look at carbon credits, yeah. And I'm concerned about monocropping, like they're looking at just koa. So I'm just wondering if the research you guys have done looks at all at just ahupua'a restoration and how much carbon does that sequester, especially if you looking at really degraded lands like on Molokai. I'm more concerned about the you know, basically protecting biodiversity and restoring biodiversity. And there's a lot of talk about ecosystem services, but are there any is there any work being done on just biocultural relationships, and how can we finance Native Hawaiian communities to restore ahupua'a? Not just looking at carbon credits, or maybe looking at that as part of the carbon credits.
Yeah, I mean, I agree. That's a major area that needs work, and we're trying to launch some projects like in that area. Because we know, right, that there's a lot of other things, that come with it, right? You look at Molokai, if you are reforesting those areas, like, yeah, you're sequestering carbon, but you're also, reducing soil export. So you're protecting the nearshore marine environment, you're yeah, probably enhancing, soil moisture and rainfall capture. So you're enhancing the aquifer and freshwater availability. You look at Lahaina, right? And the danger and the potential costs of having these fallow agricultural systems, right, that become harboring invasive species, harboring, fire-loving grasses, and, putting us at risk in a lot of other ways. And so those things are never accounted for, right? Like, once the disaster happens, oh yeah, we're somehow managed to find $500 million to finance, Lahaina restoration, but there's never 500 million to put into, hey, let's try to mitigate the risk to begin with, right? And so, I mean, to me, it's really backwards that if we put money up front, to protect our reefs, to reduce invasives, to, reforest landscapes, like, it's quite likely that the economics of it is that we save money, because then we don't have to shell out $500 million when this disaster happens or this disaster happens, and so I mean, the short answer I'd say is no, there's not, I mean, hardly any, I think, work being done in that area. But I mean, I totally agree with you. It's a super important, spot where we, to truly transform us from being, reactionary, to being proactive and, preventing disasters, right? Improving human health so we don't have, horrible medical costs and stuff associated, and um so yeah, I mean, I can't do anything except, ka ko'oyu that this is a super important area. Um, and I mean, we're trying to launch some projects in that realm, but I don't even know how you would quantify some of that stuff, right? How do you quantify the fire risk and the, disaster mitigation potential is hard. How do you quantify, right, biocultural restoration and human well-being and identity? They're like, we know they're important, and we know there's positive outcomes associated with doing the work, but how do we show that in ways that are rigorous enough that people will listen?
Is there any way to quantify the carbon sequestration of an ecosystem?
Yeah. Um,
That way we can, have the ground cover, have all the
mhm.
elements of a native Hawaiian forest without
Yeah, I
seeing
had a
high value carbon product.
Mhm.
I had a question along those lines, actually. Noah, do you see, potential for coming up with a similar study or equation specifically for the soils that say a breadfruit agroforestry, you know, the assumption is that it's going to improve soils, and we know that soils, healthy soils, sequester carbon in themselves. And so do you see potential for a similar study to come up with an equation or quantify, you know, soil carbon sequestration to then add to the tool belt, you know, for arguing for and promoting breadfruit agroforestry?
Yeah. Yeah. So to start with Malia's question, like when you look at ecosystem level carbon, you know, in terms of the plant biomass, like the carbon sequestered in the plants themselves, most of it is in the trees. Um, and um, and then you could probably, you know, if you got good tree measurements, you could like, you know, do some sub studies where you like modify the tree stuff, right? So you're like, oh, if you do trees and, you know, you have the sub canopy and the shrubs and the ground cover, right? That adds like another 20 or 30% to the tree value. And so there are, you know, ways to do that pretty simply. Um, and then yeah, and then the soil component can be really big. Um, you know, but it's important to remember, right, that it's sequestration is the change, right? So soils are a huge potential storage of carbon. But it really depends where you're starting from. Right? So if you have a healthy native forest and you cut down that forest and you do breadfruit agroforestry, you're going to be emitting carbon from your soil because like a healthy native forest is the apex, right? Like those soils are totally maxed out. But if you're like going to West End Molokai, where like all the topsoil's been lost and the soils have been beat to crap and are all degraded, right? And you do agroforestry there, you're going to be greatly increasing the soil carbon. Um, so Chad did do some preliminary soil work around breadfruit. And you know, it was pretty small study on the soil stuff, but based on the trends we saw, for instance, like in terms of the soil, it was actually better if the trees were more spaced out and there was more grass between the trees. Because trees, a lot of soil carbon comes from like the fine root material. Plants turn over their fine roots all the time. Their fine roots are dying, regrowing, dying, regrowing. And when you look at trees compared to like small shrubby stuff does that way more efficiently. And grasses are among the best. Like grasses turn over their fine root matter all the time. And so, you know, the breadfruit trees weren't contributing nearly as much carbon, even though they were dumping all their leaf litter on the ground surface. Most of that leaf litter goes back up into the atmosphere. It you know, decomposes and it you get gaseous CO2 go back up into the air. But the fine roots of the grasses get down into the soil, and when they die, they have a better chance of getting incorporated into the soil. And so I can't remember the point, but yeah, so so when you think about soil carbon, yeah, that diversified system, right, is going to be way more effective, like an ecosystem type restoration. So you have the trees sequestering carbon in the tree, but then you need all the ground cover and the shrubs and stuff like that. They're not sequestering a lot of carbon in their bodies, but they're really helping to amplify that soil carbon piece of it all. And so, yeah, so you kind of need both, right? You need the trees to store carbon in their trunks, but then you need the other stuff to start getting the soil processes going.
Hey, just like one additional point, like second everything Noah said. There is this specific to the fire risk. I'm not 100% sure of their methodology, but it's called Blue Forest. I think it's Blue Forest carbon bonds, but it's like Blue Forest bonds, and it's based in California. And about 2 fire seasons ago, in response to the electrical wires starting such bad fires there, this company, this startup based in San Francisco, they've developed a way to quantify what managing the forest for fire risk looks like and how to monetize it or whatever. And then I think the only other like thing to add is like that's a critique of this whole process is the biodiversity and valuing the natural world. Like sometimes the market's not the best for it, like because these things do have value, and just because you can't monetize it, it doesn't mean that it's not important. But if you're interested in looking more at how fire risk specifically is managed, it's Blue Forest bonds.
Thanks for that, Chad. Andy has another question in the chat about if there's an update on the tissue culture viability from the Lahaina, Ulu, and Banyan. No, I think you're muted.
Thank you. Yeah, so we've been helping out with the Lahaina, kind of trying to salvage the trees from the Malu'ulu Olele. And so there are, I believe, like 9 trees in Lahaina that are known to date back to the ancient breadfruit groves of Lahaina. And so we were asked by some community members to come in and help propagate those trees and ensure their continued survival. And so this is a picture from a couple weeks ago. And so, yeah, we were able to harvest roots from these old banyan trees. And as you can see here, they are vibrantly resprouting. And basically we take these sprouts and sever them from the roots and put them in a mist house for about a month, and we'll root them out that way. And so actually our first trees are already set to go back to Lahaina, probably within about 3 to 4 weeks. And based on what we're seeing from the roots and what we've done in the past, like we anticipate that we should be able to make, probably on the order of like 800 to 1,200 trees over the lifetime of these roots. So yeah, as soon as Lahaina is ready to restore itself to a breadfruit agroforestry, we will have the place appropriate trees for them ready to go. So I don't know about the banyan. We're not doing anything not really related to the work on the banyan at all, but the Lahaina ulu trees are definitely going to have a legacy. And yeah, the trees themselves, like in Lahaina, I would say only 2 of the remnant trees are guaranteed living and resprouting well. There's a few that are definitely dead, and then a couple that the jury is kind of still out whether the trees themselves will survive or not. But we do have their progeny, and so their legacy and their genetics will certainly live on.
Thanks for that update, Noah. I just put the link to Noah and Chad's publication in the chat. It came out as a really funky URL, but it should take you there. And we will also reshare that paper with this recording afterwards, after the recording gets downloaded. So we'll follow up with that.
And I just quickly, I threw in
nicer URL.
well, no, that's for the other paper, the breadfruit suitability that Khaleesi did. Because yeah, it seemed like there was some interest in the maps in there and the environmental parameters for breadfruit suitability.
I just have one last question before the clock hits 1. Oh, there it goes. Okay, I'm gonna ask it. So between Khaleesi's work and Chad's work, is there now enough kind of baseline data out there for a farmer with a breadfruit agroforest or orchard to potentially sell the carbon credits and go through third-party certification?
I would think so, because they're published, and I think when we did the error propagation, like, of the whole measurement scheme, like, it's still like above like a 0.85, so you're pretty accurate in terms of making those calculations. And then of course, if you're doing agroforestry, right, this is the low end, right? Because it's just the breadfruit trees, and then everything else in the system's going to be, icing on top of that.
Awesome.
So I would say yes.
Well, that's exciting. If anyone wants to get your carbon credits for your breadfruit orchard, we wish you the best of luck, but also very interested in helping.
So I will say, to wrap us up, like, I think we did it in the paper, but right, the carbon markets aren't there yet in terms of paying what it should be. So we made the assumption that, like, hey, you have to pay a third-party verifier like $2,000 every, I can't remember what we said, like every 5 years or something. And based on that and the current price of carbon, which I think on the California exchange is only like $5 per ton or something like that, you need to grow like it was something silly. It was like a 80-hectare breadfruit orchard before the carbon credits would even pay for the verification costs you would have to pay the third-party person. So, I mean, the carbon markets are set up so that only huge land holdings would even potentially be economically viable.
Yeah, thanks for that, Noah. That's a great kind of final consideration. And I think carbon markets are still somewhat in their infancy. So hopefully, as they develop, if they stick around, there'll be more quality carbon considerations that can increase that price. Yeah, thank you again, Noah, Chad, great work. Khaleesi, you as well. And have a great rest of your Friday. Have a great weekend, and we'll follow up with this recording and the paper. Aloha.
Thanks, guys.
Right.
Thank you.